All right, Chapter 8, Section 3, Similar Polygons. So here's that name similar again, and that's the overarching theme, the title, the namesake of our unit here, Chapter 8, Similarity. Okay, and so similarity is still dealing with these figures that are going to be the same shape as each other, and it's just going to be able to distinguish similarity and congruence. Two things being congruent and two things being similar are very closely related, with one slight difference. Two things being congruent are literally copy and paste versions of each other. Every measurable aspect of one is the exact same equality as the other. We call those two things congruent. And then two things being similar, it's still the same exact scale dimensions and stuff. It's just that one can be a magnified version or a minimized version of the other. And so that's important, again, when it comes to, again, that key term of scale factoring or scale modeling. So if you've ever seen a scale model where it's taken skyscrapers and reduced them down to something that can fit on your desk, or the opposite direction where you take, the same direction where you have like Hot Wheels, which are just miniature scale versions of the actual cars, or if you go to the opposite direction where you take something that would normally be very small and you blow it up. And we see that most often with, that's used a lot in movies when like a character is small and is trying to, is working in the real world, and so they've blown up things to be larger around them. There's a home off of Fox Farm up here that has extra large wooden furniture in their backyard, if you've ever seen that. But that's a version of scale modeling in the opposite direction, where you take something and you magnify it. Okay, but again, we see that kind of stuff everywhere, and so geometrically, mathematically, we give it the designation of they're similar objects in that they have some same measurements and others are scale factored. So we're going to distinguish between those two things here in this section. So similar polygons. What you can see here in this first example, again, we see that these are dilations of one another, and that term dilation is one that we talked about in Section 1 and Section 2. A dilation is considered a transformation. It changes one onto the other, or what we would say in mathematics, it maps one onto the other using a series of mathematical changes. The mathematical changes here with dilation involve a scale factor k. Okay, some multiplier, constant multiplier that's going to either magnify one onto the other or minimize one onto the other. Okay, so within two shapes that are considered similar, and in this beginning example, we're given a triangle. Okay, it does not have to be a triangle. We could be given a quadrilateral or something with more sides like an octagon. It really doesn't matter what type of shape it is. As soon as we are told that they are similar, that comes with baggage. Okay, that means the name similar has certain connotations with it. Similar is not like in English, where similar has kind of like a vague, like, oh, they're similar. They have some attributes that are like each other or like one another. Okay, in mathematics, it has very, very specific types of baggage that come along with it. And the two types of baggage we're going to talk about are these two rules right here. The first of which is this: corresponding angles. And this term corresponding is going to become very, very important. So I'll go more into detail of that in a second. But right now, let me just identify the two rules. The first of which is that corresponding angles, angle measurement dealing with degrees, corresponding angles will have to be the exact same. That will have to be what we call congruent. And that's very important because angle measurement, particularly within polygons, like these triangles that you see here, angle measurement essentially determines the shape of whatever polygon that I'm dealing with. For instance, like if I were to expand or reduce any of these angles, it's going to change the shape of the triangle. It's going to morph it into something else, warp it into something else. But if the angles match that of its dilation, then it maintains its same shape, its same kind of general feature, basically. Because I can draw different kinds of triangles. I mean, I could draw like a right triangle or an isosceles triangle, or lots of different kinds of triangles that look different than this, but are also three-sided. But the only way I get a pure dilation is if it matches those same angle measurements on the inside. Okay, so corresponding angles, whether it's a triangle like this one or something more complicated like a pentagon or a decagon or something, but corresponding angles will have to be congruent to one another. So for instance, angle A here is the same, for the term corresponding, angle A here is the same relative corner to its triangle as angle D here. So those angle measurements, whatever they were, would have to match. Okay. And the same would be true of B to E in this case, and C to F. You can see with those arches. Okay. So corresponding angles, same position angles, will have to match or be congruent. The other rule is this, and it deals with side length. So there's really kind of two measurable quantities that we're going to be dealing with. One of which being angle measurement, which does in terms of degrees. That measures how far apart two segments are in their wedge from their intersection. And then you have side length, okay, which is one that you're probably more familiar with, where we talk about length of a side. Right. So with polygons, those are going to be the two main forms of measurement that the two foundational forms of measurement that we'll deal with. Okay, so corresponding sides, and this is an important distinction right here, corresponding angles have to be congruent to each other. That's what gives that polygon that specific shape, what's going to make it a magnified version or a minimized version of its counterpart. Okay, but corresponding side length, this is where we see that scale factor applied. Okay, scale factor is going to be applied to side length. Okay, so what makes this dilation a magnification of this original triangle is the fact that I've taken each of these side lengths, as shown here by these lowercase letters. So for instance, B to C here, we'll call it side A. Okay, side A, if I want to magnify it to this larger triangle, I would multiply it by some scale factor. And that scale factor could be anything. And what we learned in section 1 is that scale factors that are larger than 1 will magnify something or enlarge something, like in this instance, where K here would likely be bigger than 1. In fact, it appears to be 2, so it would double the size, or double, in this case, the side length of that side. So if this was 5 miles, this would be 10 miles, and so on and so forth. Okay, but the important thing to understand here is that I can't just multiply any random number times a single side to get my result. Notice that that scale factor is uniformly applied to each of the 3 side lengths in this triangle. Had it been an octagon, it would be all 8 sides, a quadrilateral, all 4 sides, so on and so forth. Okay, but whatever that multiplier was, whatever that scale factor was that either magnifies, like in this example, or if it were to reduce it down to something smaller in another example maybe, whatever was multiplied would have to be the same multiplier by each of the other sides. So if K was larger than 1, like appears to be the instance in this example, it would enlarge or magnify this original triangle by that constant scale factor. And then if it were minimized, that K would be less than 1. So it'd be somewhere between some decimal or fraction between 0 and 1, whether it be cutting it in half or a quarter or a 27th or whatever. And we're going to see this notation right here. And this is a reference to what we talked about in section 1, where we had ratios or fractions that compared the distance of an image on the numerator compared to its original on the denominator. That ratio or that fraction, whatever length that would be, for instance, for segment DE, which is this side right here, okay, whatever length this turned out to be, like say maybe 10 miles, compared to AB, its corresponding side, okay, right here, if this was say 5 miles compared to the 10 miles, my fraction would be 10 miles over the 5 miles. I would reduce that fraction to find out that the scale factor K would be 2 over 1 or 2. In other words, that would translate as is doubling the size, double the scale factor to get to this guy. Okay, and so what's important with this notation right here with these 3 ratios, these represent the 3 sides of each of these triangles. It's that corresponding, there's that term again. This is kind of the running theme in this section. Corresponding refers to the fact that we're talking about same relative position within a given shape. Okay, so in some cases it's easier to spot than others. For instance, we can see just how each of these figures is oriented, that, you know, I have my long side is down here on the bottom, like this is what it's resting on, like this was a table it was resting on or something. And then this left side will correspond with this left side. This right side will correspond with that right side. Okay, this is one where it's very straightforward, but that does not necessarily have to be the case. You will not always be presented with your original figure, whichever one it might be, and its image or its dilation. They won't necessarily be oriented the same. What we learned in section 2 is that I can do a series of what we call transformations. Okay, for instance, I could take this magnified triangle right here, which is a dilation, a magnification, an enlargement of this original triangle. I could take this guy and slide it somewhere else in the free space or coordinate grid. I could take it and I could rotate it about something and turn this sideways. I could reflect this right here and flip it upside down and invert the shape down here. What will still be the case is if both the shapes are ultimately similar, both these rules will still apply. And it doesn't matter that they're oriented the same. Now, why do I bring that up? Because if they are kind of jumbled up and one's twisted and turned in some other way, shape, or form, identifying these corresponding pieces, whether they're the sides or the angles, can be a little tricky. So I'm going to basically show you some quick hints and some quick shortcuts to identify what are the corresponding pieces. Because as these are drawn right here, it's very, very apparent which pieces correspond to which, because they're oriented exactly the same. Okay, the long side is both on the bottom for both these objects. Like this top corner will correspond with that top corner. It's very, very straightforward in this case to see what corresponds to what. So let's see how that can be twisted and turned. Okay. So here will be the one example that we do today, and then we'll save the rest for tomorrow's lecture. But this is like a 3-in-1 type of thing. All right, so we are told right off the bat that two given shapes, in this case triangles again, this will be the most common shape we deal with just because you get to multiple sides and it becomes kind of redundant, the same thing that you're doing over and over again. It just takes up more space. So triangles is a nice way where you get the fewest number of things you got to put in, but you still get the general idea. Okay, it's the simplest of the polygons. Okay, so we're told right off the bat that these two triangles are, here's that symbol for similar, okay, that we learned in a previous section. The symbol for similar, in case it's a little small for you, is just like a little tilde. It's a little squiggle. Tilde for those that are in the foreign language department and stuff. Okay, but there's our symbol for similarity. Again, notice the distinction, the difference between this and the symbol for congruence. Okay, for instance, here's the symbol for congruence. Notice the equal sign underneath it. That implies that pieces are of equal measurement to each other, whereas similar does not have that equal sign. And again, that's important because, namely, side length will not be equal to the other side length. This is obviously much shorter than this one, but that's where we have that scale factor, that constant multiplier that maps one onto the other. In any case, we're told right off the bat that I have two shapes that are similar to each other. Okay, so you're not going to end up with anything weird or trick question where they're like, here's a triangle and here's a pentagon. They're similar to each other. It's impossible for that to be the case. The only way two shapes can be similar to each other is if they are the same general shape. Okay, and then as soon as they're the same general shape, in this case triangles, these two rules will apply. This is the baggage that comes along with that name, that title of similar. Okay, so corresponding angles between the two triangles will be congruent to each other, and corresponding sides will be similar to one another. They'll have some scale factor, some constant multiplier that's in common between each of the sides, in this case 3 sides. Okay, and we're asked the following questions. Part A, we're going to be asked to first identify what that scale factor is, going from this triangle here to this triangle. I'll emphasize that again when we go through this one, the fact that the direction matters. But we're going to first identify the scale factor. As with any dilation, and that's what these are of one another, these are dilations of one another. One will be bigger than the other. Okay, but what will be kind of the obvious question is that if the only change here is some scale factor, let's identify how much bigger one is than the other. Okay, and that's where we would identify what scale factor, or K, would be. All right, so we're first asked to identify what the scale factor K is, the constant multiplier that will map one onto the other. Second thing, we're going to be listing pairs of congruent angles. This will actually be the fastest one to identify. So I might actually start with this guy, and then part C will be the second fastest, and I'll come back to part A. I probably should rearrange that order for future years. But in any case, listing corresponding pairs of congruent angles. All right, that'll be the part 2 that we're asked about, which angles are congruent to one another. And since there are 3 angles, I should have 3 pairs that are congruent to each other, 3 that are equal to each other's measurements. And then finally, part C, I'm asked to make a statement of proportionality. Now, if you need to write this in your margin, what is a statement of proportionality? It's literally just as this is written up here underneath this corresponding angles, where each corresponding side is put with each corresponding side. Okay, so up here in the numerator, up here, this represented the image, the magnification of the dilation of the original. So the image goes on the numerator, and then the denominator go the original side lengths, whatever they are. Okay, and again, each of these is a ratio, a fraction, and each of those ratios will equal the others. So there's a constant, that's what this is demonstrating, a constant scale factor K. So whichever corresponding sides over which, there will be a constant between each of those sides. In this case, there are 3 sides because it's a triangle right here too. And that's going to equal whatever scale factor that we solve for part A. So again, I'll do this on the whiteboard. So here's where I'll begin. Part B and part C are very fast. Part C will take a little bit more effort just to put it in this format, but I'll walk you through that. B and C will be really fast, and we'll use our result from C to figure out what our actual scale factor K is for this part A. Okay, but this will be what I use. All right, so let me jump to the whiteboard. All right, so for this problem, we are given the following. We're given 2 triangles that we are told right off the bat are similar to one another. And that's important because as soon as I know these 2 things are similar to each other, all that other baggage comes along with it. Namely, corresponding angles have to be congruent and corresponding sides have to be scale factors of one or the other. And then it'll be important to understand the vertices, what they're titled, RST here, and then X, Y, Z. And before I write anything else that we were given for this problem, it's important to point this out. Unlike that first example that we did at the beginning of this section, these are obviously not oriented the same. In other words, it's not like this one looks kind of like it's a right angle. Notice that that's in the bottom left. That is not where it's located here. The one that looks like it's a right angle seems to be on the bottom right. So there is some sort of manipulation, movement, or transformation that has happened to take whatever the smaller version of this is to move it here. And the reason I bring that up is because what will be important to identify are what we call corresponding pieces, or what's in the same relative position. Okay, and that can be tricky in some cases, maybe not as tricky here in this example, but that is going to be an important thing to distinguish. It's not like I can pick some random side, like the left side here, and it has to match the left side here. Okay, that's not the case. But again, I'll show you how to walk through that. But then we were given the rest of this information. We were told a bunch of side lengths, and we were told that this side here was 25 units long, this one was 30, and this one was 20, and then we're told this one was 15, this one was 12, and this one was 18. And on your assignment, on a chapter test for the type of problem that you'll see here, this is what you would pretty much be given. But then we were also told this. Okay, I'll write it up here. Triangle RST is similar to triangle XYZ. Triangle RST, and again, we happen to be given triangles here. It's not necessary that they're triangles. This applies to other types of polygons as well. Okay, whether they're quadrilaterals or something like a decagon. Okay, doesn't matter how many sides. As soon as I am told that one shape is similar to another shape, corresponding angles have to be congruent and corresponding sides have to be scale factors of one or the other. Okay, and it should be quite obvious that these are definitely not congruent to each other because if that were the case, all three numbers would match all three numbers of the other one. So they're definitely not congruent. Okay, they do not equal one another. But one is a smaller version of the other. And it's pretty obvious that this is the smaller version of the two. Smaller numbers and just looks smaller. Okay, so the other thing to point out at the very beginning for part A, it asks me to figure out the scale factor from RST to XYZ. And that matters. That wording matters because that tells me the direction I'm going. The reason why? That tells me that this is the original and that this is the image from a transformation standpoint. Okay, so I'll point that out again when we get back to part A. The direction will matter, particularly when it comes to creating my scale factor ratios. But let me start with the fast parts here. And I'm going to show you the shortcut, the kind of the giveaway that they tell us just by simply writing it in this order. Okay. So part B, I said I would start with part B. Part B asks me to identify which angles are congruent to the others, because the very fact that it's told me that these two shapes are similar mean that corresponding or same relative position angles need to be matching or congruent to one another. So here is the shortcut. Again, this is part B. Part B. So let me write that right here. Part B. Again, identify corresponding pairs of congruent angles. Here's the hint. Just go in order. Exactly as it's written, reading it left to right like you would a book or a sentence, okay? For instance, what will correspond with the first letter in my shape? And again, the fact that this is a triangle, that just means that there are three corners. Had there been a pentagon, there'd be 5. Had there been a hexagon, it'd be 6, and so on and so forth. But the first letter will have to correspond to the first letter in the next shape. So the big hint here is this, okay? The way that they write these shapes, and these are basically just the name of the shape, right? The order in which they write it has to correspond with the order in the next one. That's the giveaway. So you don't have to rely on just eyeballing it and being like, all right, what piece looks like it would be? And it's a little more obvious here because you can kind of tell like, well, this one looks like it's a right angle. This one looks like it's a right angle. Maybe those are the ones that match, okay? You don't have to rely on the eyeball factor. That's a lot trickier when you have something like, say, an isosceles triangle, right? You might come across one of those hints. So in any case, the giveaway for what corresponds to each is just go in order. First letter corresponds with first letter. Second letter with second letter. Third letter with third letter. Pretty much as easy as that. So the answer for what angles are congruent to each other, R will have to be congruent to X. So angle R is congruent to angle X. So what looked like a right angle here does in fact match with what looks like a right angle here. Okay, that doesn't mean that they're actually right angles. In fact, they're probably not because they explicitly did not write that little right angle perpendicular square thing. But angle R and angle X will have to correspond to each other, and thus, because they're similar, have to match each other. All right, now there are 3 pairs of congruent angles, so I'm just going to keep working down the line. So first matches with first, second matches with second, so S and Y have to be corresponding angles. And lastly, third with third, angle T has to be congruent to angle Z. And again, had there been more sides to my shape, I would just simply work down the line. Done for part B. So again, the massive hint, the part to take away from this day's lesson is that I'm just going to go in order. First goes with first, second with second, third with third. I'm actually going to use the same strategy for part C, where I'm asking about creating a statement of proportionality as well. So let me scroll down a bit for that. All right, for part C, they ask me to make a statement of proportionality, which is essentially this, but it's going to deal with side length. So I'm going to be talking about segments here. Okay. The other piece to be aware of here is just to kind of keep some uniformity throughout this example, referencing back what was said here in, let me just show the notes page really fast so I can just point it out. Okay, just pointing this out in part A right here, notice that it says find the scale factor from RST to XYZ. That order matters because that tells me this is the original and this is the image. That will matter particularly when we come back to that for solving for what K is. Might as well keep that uniform for part C here. So again, let me just make a little note of this. Because it said to go from this RST to XYZ, that tells me that this is the original shape and this is the image shape. Again, that will matter, kind of referencing back to section one. Section one, we talked about dilation and scale factor. The idea that for that ratio of what makes K, that scale factor, is that image values, image measurements will go in the numerator, original measurements will go in the denominator. So we'll keep that uniform here. But in any case, what I'm going to need to do is I'm going to need to figure out, like, okay, side RS right here, which side does it correspond to here? And again, in this case, it might be simple enough to identify which piece is going to correspond to which piece. But my massive hint here is that I can, again, just go in order. So for instance, RS, the first two letters here, have to correspond to the first two letters here. RS has to correspond to XY. And so just to keep uniformity here, I'm going to put image values in the numerator. So for instance, I'm going to start actually with XY, XY image being in the numerator. So XY in the numerator is going to correspond to the first two letters, 1 and 2 letters of the other triangle, in this case, RS. If I were to actually take that value, that 12, and then divide by the 20, that would give me my actual scale factor. For the statement of proportionality, that scale factor is going to match each of the other ratios of each of the other two sides. So let me just make my way around. So if I went from XY, let me just go this way to now YZ, okay, or my second and third letter, YZ in its name, to the second and third letter of the original. YZ has to correspond to ST. YZ, ST. There's side number 2. That needs to equal the ratio of the third side. And now I have ZX, okay, or third letter back to the first letter, third letter back to the first letter. So ZX will correspond to TR. Okay, so there's all three sides, and whatever that equals, whatever each of these equals, has to be the same thing. Each of these ratios has to equal the same thing. Image measurement on the top, original measurement on the bottom, that's going to equal my scale factor K, whatever that equals. So now for part A asks me to actually solve what K equals. So let me now go back to that, because now it doesn't matter which of these three ratios I use. Any of the three will be the same exact thing. I could go through confirming that, but that's just time consuming. So let me start with just this first one, XY over RS, image over original. XY is 12 units divided by RS, the original corresponding piece, being 20 units. So now, again, just scrolling down a little bit. So now I'm coming back to part A. Again, I need to change this for future years, the order. For part A, where it asks me to identify what is that scale factor K, where scale factor K, again, represents some image measurement over its original measurement. And it did tell me to go from RST to XYZ, meaning that XYZ measurement should be in the numerator. So we'll use XY. It doesn't matter which of the three I use, but we'll use XY being 12 units. Okay, that 12 units for XY over the original amount for RS being 20 units, this will represent my ratio, 12 over 20. Okay, and again, I could have used YZ over ST being 18 over 30. I could have used ZX over TR being 15 over 25. It doesn't matter which of the three, all three of them should reduce to the same thing. Because when I reduce this, 4 goes into top and bottom, 4 goes into 12 3 times, and 4 goes into 20 5 times. There's my reduced fraction. My scale factor is 3/5. And that makes sense because RST was a larger version of XYZ. So if I'm going from the large to the small, it makes sense that my scale factor is less than 1. 1 here would be 5 over 5. Okay, and so just really briefly, just to prepare you for what you might see on big ideas, for part C here, where it's asking you for the statement of proportionality, What it might want you to do here is put 3/5 or whatever you solve for k in for k. So just be prepared for that. Okay, so again, the major theme to take out of this for today is that there are corresponding or relative same position pieces, because it's not always the case where you're going to be shown the original and its image oriented the same exact way. And if you are shown it that way, then it's very straightforward. You just look like, all right, bottom left to bottom left, upper right to upper right, so on and so forth. Where if it's any way, shape, or form kind of reoriented like these two are, then it will be helpful to just kind of go in order, reading it as they are. R goes to X, S goes to Y, T goes to Z. That's how you can figure out corresponding pieces. And that's where I'll go ahead and stop recording.